Okay, so in our previous video we introduced the idea of maximum or minimum applications or optimization problems, and today we want to continue to look at those, but I just want to broaden our understanding slightly of what happens at the third step. We were a little bit narrow previously, and we want to broaden it to think about not just turning points, but actually where is the absolute maximum or minimum point of the function. So the steps are the same. The first thing is to identify the quantity to be maximised or minimised. The second step is to construct a function to describe that quantity. So remember, that's the hardest step. And the next step, the third step, is to find the maximum or minimum point on that function. Okay. Now, in the previous video, we really just focused on the maximum or minimum point occurring at a stationary point. So we looked at where derivative was 0, we justified we had a maximum turning point, and therefore we're able to find that was the x value that gave maximum area, volume, cost, time, whatever. Okay. But what we actually need to think about is that the maximum point, or the highest point on a function, doesn't necessarily happen at a turning point. Okay. It will happen at a turning point if you have a function with only one turning point and that turning point's a maximum. Because if your function only turns once and that's a maximum turning point, it can't get higher again because it can't turn back around to come back up again. Okay. Same logic for minimum. Okay. But if you, for example, have a cubic function, this is a maximum turning point, but there are much higher points on the graph up over here. Okay. Same with the minimum. This is the minimum turning point, but there are lower down points on the graph than here. So, if you're measuring, cost and whatever, and you're trying to minimize cost, and you've got a function that does, now bearing in mind we're not going to have negative cost possibly, so let's say our function sort of, does this, the minimum turning point, that doesn't give you the minimum cost, because there's actually all these points over here where the cost is lower. The cost is actually lowest here. Okay. So you need to actually think more fully about the function that you're dealing with. You do still need to consider turning points, because it might still be true. It might be a cubic, but it might still be true that you're looking at this part of the cubic and that's still the minimum at the turning point. Okay, but it needs to be considered in conjunction with some endpoints of the function and a sense of what the function looks like. So, as I said, derivative calculus is still relevant. The local maximum and minimum points are still important to be considered, but you also need to consider those against other points on the graph as to whether they are the minimum point of the graph. Right, so let's have a think about this function then. It is a quadratic with equation x squared plus 2 over a restricted domain from -2 to 4. We want to find the absolute minimum value of f, or state, we've got all the information we need in the graph, and the absolute maximum value of f. Okay, so the absolute minimum value of f clearly happens at the turning point. This is the lowest value of f. There's no lower y values, but the absolute maximum value of f doesn't happen at a turning point. It happens at an endpoint, and it happens at this particular endpoint. Okay, so we know that the absolute minimum value of f is f at 0. It is the y coordinate at 0, and that is 2. We know that the absolute maximum value of f is the value of the function when x equals 4. This is going to give us our maximum value, and so we're actually going to need to work that out. We haven't been given the coordinates of this point, but we have got our rule, x squared plus 2, so f of 4 is 4 squared plus 2, so that's 16 plus 2, which is 18. So 18 is the maximum value of this function, and therefore the maximum value of f. Okay, so let's have a look at some examples. Less about context. I'll do one with context today, but I just want to talk a bit about this idea of an absolute maximum and minimum value. So find the absolute maximum and minimum values of this particular function here. So it's a quartic over a restricted domain though from 0 to 4. So we really need to think fully about what this graph looks like. What's the shape? Any x-intercepts turning? You really need to sketch it, to be honest. Okay, so let's have a look at, I'm already seeing that the y-intercept is going to be at 0. Because if I let x equal 0, y will be 0. X-intercepts are fairly easy here. 2x to the power of 4 minus 8x to the power of 2 equals 0. Nice common factor of 2x squared leaves me with x squared minus 4. And so we would get 2x squared equals 0, which means x squared equals 0, which means x equals 0. You could just go straight to x equals 0. or x squared minus 4 equals 0. So x squared equals 4. So x is positive or negative 2. Okay, so let's think about what that looks like then. So it's a quartic, positive quartic. X-intercepts at 0 and plus and minus 2. So it's going to look like this. Let's try and get that symmetric. Try that again. It's going to look something like this. Wasn't much better, but it's a bit better. Except we're only interested in it over the restricted domain, 0 to 4. So we're actually only interested in this bit of it. Okay. We also want to think about, so if we were going to sketch it, we wouldn't be sketching this bit back here. So this bit wouldn't be there. We would just be sketching this shape here. So turning point at the origin. That's the point 2, 0. So actually I'm going to need a bit more space because I want to go up to 4. So let's have 2 and 4. And we're going to need to move that down. 2 and 4. And perhaps just be a bit careful about how low down we go here so that we can fit it on. I'm going to keep going all the way up to 4. Okay, so that's the point 2, 0. This is the point 0, 0. So we can see that the absolute minimum value is clearly happening at the turning point. So we're going to need to find that, but we can see that the absolute maximum value doesn't happen at a turning point. This function has a maximum turning point. It was there at 0, but that's not the absolute maximum. It gets higher than that. There's the absolute maximum value up there. Okay, so we know the absolute maximum is the y value when x equals 4, so that's f of 4. We know the absolute minimum value will be the y value of the turning point, so we actually need to find the turning points. So let's find the turning points. So let's find the derivative, which is going to be 8x cubed minus 16x. We want to solve that equal to 0. It's a polynomial, so we want to try and factorize it. 8x is a common factor, x squared minus 2. So that's going to give x equals 0. This will give x equals plus or minus root 2. Okay, so this is clearly root 2. So it's the y coordinate of that point that's going to give us our absolute minimum value. Okay, so the absolute maximum is f at 4, which is 2 times 4 to the power of 4 minus 8 times 4 squared. Apologies if you can hear some background noise. My washing machine is going through a vigorous period of its cycle. So what have we got there? 2 times 4 to the power of 4. 4 cubed is 64, and to the power of 4 again is 256. Minus 8 times 4 squared, minus 8 times 16. So that is 512 minus 8 16s, 8 10s are 80, 8 6s are 48. So that is minus 128. And that's going to be 512, 412, 384. Okay, so the absolute maximum value is 384. That's this y coordinate up here. The absolute minimum value is going to be the value of our function at root 2. Okay, so that is 2 to the power of root 2 to the power of 4. Sorry, not 2 to the power, 2 times root 2 to the power of 4 minus 8 times root 2 squared. Now, if you do a square root to the power of 4, I'm just going to write up here for a minute where I've got some space. So root 2 to the power of 4 is root 2 times root 2 times root 2 times root 2. Now we know root 2 times root 2 is 2. Root 2 times root 2 is 2, so we actually just get 4. The other way you could think about this, you could think about it using fractional indices. So root 2 is 2 to the power of a half, that to the power of 4, multiplying those powers, half times 4, so we get 2 squared, which is 4. Okay, so root 2 all to the power of 4 is 4. So that's going to be 2 times 4 minus 8 times, obviously root 2 squared is 2, so that's 8 minus 16, so it is negative 8. Okay, and so that is our minimum value. Okay, so considering fully both the turning points and the endpoints to see whether, as I said, you've got a maximum turning point here, but it's not the absolute maximum value of the function within this particular domain. Now, obviously, if we didn't have a domain here, this function doesn't have an absolute maximum value. It gets bigger and bigger and bigger. So you're not going to be asked for absolute maximums or minimums where there isn't actually an absolute maximum or minimum. Okay, let's go back to a problem with some context. So a farmer has 200 metres of fencing to enclose a regular area adjacent to a river. So 3 sides of the area need to be fenced, and the 4th side is bounded by the river. Okay, hopefully by now you've done quite a lot of examples along this line. We've seen examples like this back in the polynomials topic as well, in term 1. So 3 sides of the area need to be fenced. Okay, so we're fencing a rectangular paddock against a river. What is the maximum area he can enclose if the region cannot extend more than 40 metres from the river? Okay, so let's call that x. Let's come up with a way to describe that in terms of x. Okay, so we already know, if we call it y for now, we know that y plus 2x has to be equal to 200, and so therefore y is 200 minus 2x. Okay, so this is 200 minus 2x. So if you can get to a point where you don't actually need to introduce another variable, that's great. Okay, so we also know though that we've got a restriction here that we haven't had in these examples in the past. So the region cannot extend more than 40 metres from the river. So we know that x, obviously it has to be positive, but it also can't be bigger than 40. So we've now got a domain that we need to be a bit careful about. Okay, so we're trying to maximise area. So we want an equation for area. So we know that area is going to be x times y, which is 200 minus 2x. Okay, you can write that in many different ways. You can expand it. You can fully factorize it, which the top line wasn't fully factorized. Sorry, I don't know why that's 400. It's just 4x squared. I don't even know why it's 4. Sorry. It's 2x squared. Okay. You can take out 2x is the common factor. That's the highest common factor. So fully factorized, it's actually just 2x times 100 minus x, however you want to do it. Okay, now again, this is a quadratic, so I actually don't need derivative to find turning points, and I don't need a lot of work to draw this graph. I can see that it's a sad parabola. I can see that from here as well, and I can see that it's got x-intercepts at 0 and 100. So I know that it is that, okay? But I only want to draw it from 0 to 40 because of this restriction. Maybe there's a big tree here or something. It means we can't, that's why we can't build it out further than that. So we're actually only looking at this graph from 0 to 40. Okay, and the reason I know that 40 is before the turning point is because if this x-intercept is 100, this turning point is clearly at 50. Okay, so I only want to go to 40, and I want to find, are we trying to maximize the area? Maximum area, so the maximum area will happen when x equals 40. So max area, so that's our maximum area. This axis is our area axis versus our x-axis. Max area is when x equals 40. So that means that area max is, let's put 40 into our equation. I don't mind which one we go into. I might go into the last one. So it's going to be 2 times 40 times 100 minus 40. So that's going to be 80 times 60. So 6 8s are 48 and 2 zeros, so 4,800 meters squared is the maximum area that I can fence. Okay, example 3. Now let me just be clear, I answered all those questions. Actually did it ask for the dimensions? What is the maximum area he can enclose? Yeah, okay. So if it asked, and what are the dimensions of the paddock, then obviously it's 40 meters by 200 minus 2 times 40 by 60 meters. Apologies, I think I just said it'd be 40 by 60 meters. It won't be 40 by 60. If x was 40, the other dimension would be 200 minus 2 times 40, which is 200 minus 80, which is 120. So the actual dimensions of the paddock are 120 by 40, which is also where our 4,800 comes from. Okay, let's have a look at the third example. This follows the same process as many problems that have context. And again, it's still about what are you trying to maximize or minimize, come up with an equation for that with only one variable in it, find the maximum point, etc. So find the possible value, so for the variables x, y, and z, it's known that x plus y is 75 and z equals x times y. If x can only be between 20 and 50, find the possible values of y. Okay, so let's think about how y and x connect. So we know that y is 75 minus x, okay? Now, you can probably think about this domain and this rule pretty easily without needing to think about a graph. 75 minus x is obviously a linear graph with a gradient of -1 and a y-intercept at 75. And if you're only interested in it from 20 to 50, okay, it's clear you're going to get maximum y when x is equal to 20 and minimum y when x is equal to 50. Okay, so max y is going to be 75 minus 20, so 55, and minimum y is going to be 75 minus 50, so 25. Okay, so possible values of y. Y can be an element of 25 to 55. Find the maximum and minimum values of z. Okay, so we know that z is equal to x times y. Let's get z just in terms of one variable, so let's get it just in terms of x. So let's substitute this in here. So z is x times 75 minus x. Okay, now that's a quadratic. It's a sad quadratic again, with x-intercepts at 0 and 75. Okay, and we know that x can only be between 0 and 50. Now, to think about where the turning point is here, again, we don't need calculus here to find the turning point, but if it's a more complicated function, yes, you would use some calculus. Half of 75 is going to be 37.5. So if we know that x is from 20 to 50, okay, so x is from 20 to 50, so sort of something like that, okay. Right. So x equals 20 maybe is, so that's 17 and a half less than 37, whereas 50 is only 12 and a half more than 37. So again, if you think a bit about the graph, it can be clear which of the endpoints is actually lower than the other one. I know that 50 is closer than 20 is to the turning point, and so therefore 50 will be higher up, whereas 20 will be lower down. So in terms of thinking about the maximum and minimum values of z, okay, so we know that, remembering this axis is z and this is x, so we know that max z is at the turning point, okay, so z max is our function at 37.5, so it is 37.5 times 75 minus 37.5. So I'm just subbing 37.5 into my rule. So that is 37.5 squared. I'm just going to get my cows to do that for me. So that is 1406.25. There's no units here because there's no context. Whereas the minimum z, min z, is when x equals 20. Now, if you hadn't drawn a graph, you would need to think about the two endpoints. You'd need to calculate what does z equal when x is 20 and what does z equal when x is 50. But if I've thought about the graph and I know that 20 has to be lower down than 50, and so therefore I'm only going to worry about 20. So min z is when x equals 20, and so when x equals 20, subbing into our rule, that's going to be 20 times 75 minus 20. So that is 20 times 55. 2 times 55 is 110, so this will be 1,100, whatever the units are. Okay. So just adding into that step where you then want to find the maximum point of a graph, adding into that step the process of thinking about the endpoints, so not just thinking about turning points. Now, other thing, obviously, if we've got CAS, we can use CAS to help us with derivative, etc. But the CAS also has two functions called function max and function min. So if I think about, let me just define this particular function I just did here. So if I define z of x as being, z of x as being equal to x times 75 minus x, then if I use function max, so menu 4 for calculus, 8 function max, and tell it, I want you to find me the maximum of z of x. Now you always need to put comma x or comma whatever the variable in the function is for f max. And if I want to find the function max over a restricted domain, I'm going to give the domain. Now in this case, the function max, this is a quadratic, the graph never gets any higher than this, so that's actually the maximum of the function. So if I didn't put a domain, it would tell me. It happens when x equals 75 on 2, which is 37.5. Okay. So I don't actually need the domain here, whereas if I ask it, and obviously then if I want to know what the actual maximum value is, it only gives me the x value of where the maximum occurs, so then you would need to sub that back in. So you would need to do z of, 37.5, or 75 on 2. Okay. If I did function minimum, so menu 7 for function minimum of z of x with respect to x, if I don't give it a domain, it's going to tell me the function minimum is when x equals positive or negative infinity, and that's because the parabola goes on and on forever and it gets lower down here. So I want to know the function minimum over the domain, so given that 20 is less than or equal to x, sorry, the washing machine is really getting excited now, less than or equal to 50. And then it will tell me that the minimum is when x equals 20. So if this is not as simple, the function is not as simple, or I haven't sketched it and I'm not sure which endpoint the minimum might be at, or whether it might be at a turning point, it'll tell me the minimum's at 20, and therefore then I just need to sub 20 into my function to get my minimum value. So maximum, minimum, obviously derivative also useful. So you could solve your derivative, again, if it's not a quadratic, derivative of z of x. I mean, you can solve it for a quadratic, but it's a bit trivial. Equals 0 for x. It'll tell you your turning point is at 37.5. Sub that back in, etc. But function min and function max can also be a useful tool to have in your tool belt when solving max min problems. Okay, so today the work is from exercise 18E. So again, working on being able to formulate the problem, but also focusing on the fact that the maximum or minimum point of that function might not be at a turning point, it might be at an end point. So thinking more fully about the function at that step.